Okay, let's get started. We missed a lecture last week because we had this national holiday, but today we're back in business, and as the saying goes, show must go on. Well, I can tell you something curious. At our first lecture, when I cited some examples of events that involve uncertainty, among other things, I mentioned the possibility that the train gets stuck in the underground and I miss my lecture. And I said that I really hoped it wouldn't happen to me while I'm doing this course. Well, this almost happened today. The train that I took was stopped at one of the train stations, and all the passengers were evacuated, and there was this terrorist threat, I think. They were looking for a bomb or something, which was why I had to take a roundabout route to get here. And I'm a bit late, and I'm all excited and all hot. So, well, the reason I'm telling you this is things happen, and we can't foresee everything that happens to us. All right, back to our studies. Now, I think the last thing that I did at our latest lecture was this theorem. I'm going to reproduce it here again because it's so very important. Well, suppose x1, x2, xn are independent identically distributed random variables. Now, there is a notation for it. Independent identically distributed, there is this shorthand, IID, independent identically distributed, because in probability theorem and statistics, we often introduce this condition. So suppose x1, x2, xn are first independent and second identically distributed. Then, if we consider this random variable that is a function of x1 to xn, and it's called x bar. Okay? So this is a standard notation. It's read x bar. And by definition, x bar is the average, arithmetic average of these n independent variables. Then we can say something very important about x bar. First, okay, I continue here. The expectation of x bar. Oh, okay, just a second. Let me get back to this point, and let's assume that. Well, because they are identically distributed, they have a common mu and a common sigma. So let's denote this common expectation by mu and the common standard deviation by sigma. Now, expectation of x bar that is formed in this way is just equal to mu. Okay, it's equal to the individual mean, the mean of an individual random variable. Well, this is more or less to be expected. The second part of this theorem is not so obvious, and it's absolutely important. It's actually the foundation of all the methods in statistics, or most of the methods in statistics. Well, did we discuss a proof of this? is there a single person here who remembers whether we discussed a proof of this? Because I don't remember, I must admit. Well, okay. There is no harm in repeating this, okay? Let's discuss a proof of this second part here. Proof. All right, let's write this. Variance. What is variance over X bar? Look at this. We can look at this average look at this as a result of two operations. First, we add up n identically distributed random variables, and then we multiply by the factor of 1 over n. Okay? And one of the statements that I made last time was that a constant factor can be taken out from the variance, but if we do this, we square it. Okay, that was one of the things that we discussed. So we can take out 1 over n, but it takes a square. Okay. And the next thing is this: the variance of the sum of independent random variables is equal to the sum of the respective variances. And that was, again, something that we already discussed. And this is one of the assumptions that we make here, that x1, x2, up to xn are independent. Okay? So, and not only they are independent, they are identically distributed. So they have a common variance. And here we have the sum of n copies of this variance. Okay? So it's going to be 1 over n squared. And here we can write n times sigma squared. Okay? Are you following me? This results from taking out this constant coefficient, 1 over n. And this results from our assumption that these random variables are independent. Okay? And we can factor n once. Okay? Here it's 1 over n squared. And the result will be sigma squared over n. And this is variance. Okay? Taking the square root of this, we get what we expect to get. Sigma x bar is equal to sigma divided by the square root of n. Okay. Now, let's try to comment on this in simple words. Again, this is an all-important fact in probability and statistics. And the fact is this: if we have independent, identically distributed random variables, then the operation of taking the arithmetic average, this, creates a random variable that has the same mean, this, and a sigma, a standard deviation, that is this many times smaller. Okay, so sigma x bar is actually a smaller value than sigma. Okay, it's obtained from sigma by dividing by this square root n. Okay. Well, okay, and let's give it an example. Well, suppose we perform measurements. We have a certain instrument for measuring a certain meaningful quantity, and we perform measurements. Okay? Well, such as length or weight or something, some physical quantity. All right, but there is no such thing as perfect measuring instrument. Any instrument produces some errors of measurement. Okay, errors. Okay. Well, suppose we perform n measurements, and the errors Let's denote the errors by x sub I, okay? x1, x2, and so on. Okay. Well, let's assume that the measurements are independent. We assume independence. This is an important point. Question. Provided we can ensure independence, can we somehow improve the result of our measuring procedure in terms of error? Can we make the error smaller than the error typically created by this measuring instrument? Well, I'm just giving you an answer to this. The thing to do is to perform a series of measurements and then take the arithmetic average. Okay? Now, if these measurements are independent, then the errors are also independent. And if we take the arithmetic average of the measurements, the errors are also subject to the same procedure. Okay? The resulting error is the arithmetic average of the individual errors. Let's denote it by x bar, and this is, okay? Well, and look at this. If let's write it here, we assume that mu is 0 for x's, for these x's. What does it mean in simple words? We assume that our measurements do not produce any systematic error, okay? And this is exactly the way to write it. The expected value of an error is 0. The same thing is expressed by saying that there is no systematic error, okay? And and look at this. For x bar, the distribution is again around 0, and sigma of this distribution is square root n times smaller than sigma on one individual measurement. This is an effective procedure. It's actually quite realistic. But there is a reservation to make here. Look at this. We assume that we are capable of performing independent measurements. It's a tricky point, okay? It's actually it's a big question whether we can ensure independence. But mathematically speaking, if this is in place, then the rest works beautifully, okay? All right, next. Law of large numbers. All right, let's ask this simple question. Suppose we perform a random experiment that produces a certain random variable. Suppose we reproduce the same experiment n times and compute this average of the values, x1 plus x2 plus xn divided by n. Well, if n is increased, if n goes to infinity, what do we expect of this arithmetic average? Well, on this simple intuitive level, we can say that we can expect it to converge to mu. Well, it would be very strange if it weren't this way. Then our whole intuitive understanding of probability theory would be undermined, okay? So we expect that the arithmetic average of many copies of the same random variable will approach its expected value. This is our intuition. Well, and luckily, this theorem gives a positive answer to that. But this positive answer is not so simple. It's probability theory. It's not Newtonian mechanics. So the answers given by probability theory, well, are much more subtle and sophisticated than given by Newtonian mechanics. All right, theorem. So let x1, x2, xn be iid. Be iid. Let these random variables be identical, independent, and identically distributed with mean mu. Okay. Then, for any positive epsilon, now this is a lowercase Greek letter epsilon. By tradition, this tradition comes from calculus, actually. Originally, it was a tradition in calculus to denote a small infinitesimal quantity, a quantity that is going to be indefinitely small. Well, epsilon is used to denote this kind of thing. All right, so for any epsilon, any positive epsilon, and although we do not write it explicitly here, but we keep in mind this, for any positive epsilon, however small, okay? It's not written explicitly, but this is actually what we mean by this. For any positive epsilon, the limit as n approaches infinity of the probability of x1 plus x2 and it's less than epsilon equals 1. Now let's try to understand what's written here. These vertical lines indicate the absolute value. So in the middle here, we have the absolute value of the distance between this x bar, the arithmetic average, and mu. Okay? And then we have less than epsilon. So for any positive epsilon, the probability that this deviation of x bar from its mean is less than epsilon approaches 1 as n approaches infinity. Well, a simpler way, but not a formal way to write it is this. X bar approaches mu as n goes to infinity, well, in probability. Well, this is, in probability theory, there are more than one type of limit, okay? And this is one of them. This is called convergence in probability. So x bar converges to mu in probability. This is the right thing to say. And in full, what we mean by this convergence in probability is written here, okay? Well, if I try to put it in even simpler words, I would probably say this, that the deviation of x bar from its mean becomes, well, no, it's, I warned you, it's a bit tricky. Now, it's a bit difficult for me to find the right words. The probability that the deviation of x bar from its mean is greater than some given epsilon goes to 0 as n approaches infinity. So it becomes less and less likely as n approaches infinity. Okay, try to give it some thought, and I hope it will sink in. All right, we are not going to discuss a proof of this. We just don't have the time, although it's not technically. Well, let me tell you, that was a great step, a great achievement in probability theory, because this theorem answers a lot of questions and lays a foundation for many further methods and theorems. But technically speaking, it's not very difficult, and we would be able to discuss it if we had more time. Let me just try to give you an idea of how it is proved. Do you remember the Chebyshev's inequality? Now, if you try to recall what it says, what it's about, now Chebyshev's inequality tells us that a random variable cannot be very different from its mu, from its mean, if the distance between the random variable and mu is measured in sigmas. Okay? This is a very informal way to put it. But so x cannot get very far from mu if the distance is measured in terms of sigma. This is one part, one thing that is used in this proof. And the other thing is just this, Sigma x bar goes to 0 as n approaches infinity, okay? So putting together these two pieces, we get this, law of large numbers, okay? If you're interested, please look it up in some textbook. And we have to move on. All right, there is, x bar, again, has this fundamental properties. Its expected value is the same as the value of an individual variable, and its sigma goes to 0 as n approaches infinity, following this law, okay, 1 divided by square root n. But it's not the whole story. X bar has another wonderful property, and this other wonderful property is the second half of the foundation of statistics. It's called the central limit theorem. I think at our latest lecture, I kind of gave you an advance statement of this, okay, an informal statement, just to direct your ideas in this direction. And now we are going to discuss a formal statement. So it's central limit theorem. So it has a name, central limit theorem. Well, let x1, x2, xn be IID, and you remember that it stands for independent and identically distributed with mean mu and standard deviation sigma. Then well, in this theorem, we'll look at the difference x bar minus mu. X bar minus mu. It turns out that if this difference or deviation is multiplied by square root n, then the limit of this quantity as n approaches infinity is a normal random variable, okay, with mean 0 and standard deviation and variance sigma squared, or standard deviation sigma. Well, this is absolutely marvelous, because we do not, the main thing about this theorem is this: we do not make any assumptions about the law, the probability law, the distribution that these random variables follow. We absolutely do not assume that it's normal or anywhere close to normal. Okay, the distribution law of these random variables can be of any kind whatsoever. Okay, And if we, the conditions that we make are totally different. It's not some assumptions about the law. It's the assumptions that they are independent and identically distributed, no matter what this distribution is. Okay? And it turns out that the deviation of x bar from the mean is, in a certain sense, described by the normal distribution, by an appropriate normal distribution. The exact formula is written here. Okay? So, well, it's not enough to take x bar minus mu. It's not normal. But if we multiply it by root n, what we get is, in the limit, we get a normal distribution. Okay? Well, and an equivalent formulation of this is limit n approaches infinity, x bar minus mu, sigma root n is n 0, 1. Okay. Now, I think I introduced that notation at one of the previous lectures. N capital stands for the normal distribution, and here we state two parameters. The first parameter is the mean, and the second parameter is the variance. Considering this, what do we have here? N of 0 and 1. This distribution has a special name. Do you remember this? Well, it's called the standard normal, and the standard normal plays an outstanding role in probability and statistics. So, look at this. If we take this deviation, x bar minus mu, and divide it by sigma over root n, then the limit of this complex as n approaches infinity is just the standard normal, which is absolutely stupefying why it should be this way. Okay? But this is the nature of things. And this explains, actually, this explains why the normal distribution is so widely observed, so often observed in nature and in economics and everywhere. Okay? Because it results from, it appears as the result of a great number of random variables acting together, summing up. Okay? And because this happens all the time, the normal distribution appears all the time. It explains why it's so very important. Okay? Well, let's take a couple of simple examples. Example. Well, U, I think we use this notation for the standard uniform random variable. Okay? And the standard uniform random variable, it has mu 1/2 and sigma squared equal to 1/12. The variance is 1/12. All right. Using this, now, what I mean to say by this example, do you remember what kind of distribution this is? Does it look like the normal distribution? It's probability density function. Okay, like this. It's a line segment, a horizontal line segment. It's nothing like a bell-shaped curve. Absolutely no resemblance at all. It's not symmetric about, well, it is symmetric about 1/2, but the rest is just very, very dissimilar from the normal distribution. And although this distribution does not at all look like normal, and it doesn't look promising in terms of creating a normal distribution somehow, and still, suppose we take a large number of independent duplicates, copies of this random variable, then and take u bar, the arithmetic average, then the limit as n approaches infinity, root n u bar minus 1/2 equals, and well, if I may write it here, I'm not sure you can see it properly. Now, according to this theorem, using the first of these two formulations, the limit must be n, the normal distribution with 0 mu, okay, and sigma squared and the same variance. So it's 0 and 1 over 12. Well, by the way, you can perform an experiment and see how it works. You can use the Excel, and the Excel contains this built-in function, R, A, and D, and a pair of parentheses that do not contain anything, okay? I think some of you have already used it on my practice course, computer practice course. So you can, and this function generates exactly this standard uniform. So you can generate a lot of copies of this, take the arithmetic average and do it many times and see whether you arrive at a normal distribution. It's an interesting experiment. Well, by the way, if you find out that you do not arrive at a normal distribution, what would be the implication? What would that mean? Well, it would mean that the random number generator built in Excel is not very good. Because in theory, this should converge to the normal distribution. If it doesn't, it may be considered as an indication of some deficiencies in this random number generator. Okay, another example like this. Example. Okay. Let's take the average of n Bernoulli trials. So x, each variable x, x1, x2, up to xn is a Bernoulli trial with mean p, probability of success, and sigma squared equal to p times q. All right, let's just, for the sake of difference, let's take this other formulation here. The limit as n approaches infinity, and here we write this, x bar minus mu, which is p. P is, again, the probability of success on an individual trial. And what do we write here? It's sigma divided by square root n. Now, this is not sigma, this is sigma squared. So what we have here is square root of p times q over n. And this is the standard normal distribution. Again, you can find some appropriate means in Excel to perform an experiment, okay, and see whether it works. All right. Let's go on. Now, let's ask ourselves this question. For some reason, well, you may have this impression. What's the point of making it so messy, so difficult, so complex? Let's ask this question. Suppose we have x1, x2, xn that are IID. And well, we do not assume that they are normal or something. We just assume that they are independent and normally distributed. And let's consider just the sum, not the average, not x bar, just the sum. Okay? Well, from what's written here and here, it seems to follow that the sum must approach the normal distribution where mu is n times mu. Okay, we assume that this has mu and sigma. So we take a row, a sequence of independent identically distributed random variables, well, with the same mu and the same sigma. and let's take just the sum, not the average. Well, the mu of the sum must be n times mu. Okay? And the variance of the sum, if they are independent, is the sum of the individual variances. And because they are all the same, it's n times sigma squared. So the question is this. Is this correct? Well, can we say that the sum of a large number of independent, identically distributed random variables approaches the normal random variable where mu is n times this individual mu, and sigma and variance is n times the individual variance? Is that true or not? Well, it's important to understand this. Now, actually, the answer to this is yes and not, and no. Okay, and why is it yes and why is it no? The yes part means that if we take a large number of independent, identically distributed random variables and sum up, then the result, this sum, is really close to this random variable written here, normal random variable. But there is a catch here. There is a subtle point. It's not correct to say that this random variable approaches this right-hand side random variable as n goes to infinity. And why is it not correct? What's written here is not something definite. It's not just one random variable. As n increases, the center of the distribution, the mean, shifts to the right, proportional to n. And again, as n increases, the variance increases proportional to n. So as n increases, this distribution shifts to the right and spreads out. Okay? So we cannot talk of convergence in any strict sense, in any mathematical sense here. But it doesn't mean that we can't use the right-hand side as an approximation to the left-hand side. So for a given n, if n is large, the left-hand side can be expected to be close to the right-hand side, and the larger is the n, the closer the two can be expected to be. All right. And another thing. Well, before I write this, let's just, in verbal form, let's cite an example of this. Well, these elevators that we use here in this building, if I'm not mistaken, there is a warning on the wall that the number of passengers should not exceed 10. I think it's 10. On the other hand, it's written on the wall that the total weight should not exceed 1,000 kilos. Well, I'm not sure about these figures, okay? But something like this is actually written on the wall of the elevator. Now, we can treat this little problem mathematically now, okay? Suppose we have a distribution for the random variable that is the individual body weight, okay? Now, when we sum up, then we assume that people that enter the elevator do it independently of one another, okay? I mean, young and slim students don't arrive in groups, and old and fat instructors don't arrive in groups, okay? Because this would make all our reasonings absolutely groundless. So this is the second part is important, the part about teachers not arriving in groups. All right, if passengers arrive independently, not by category, okay, then we can apply this. We can, well, 10 is not a large number, but for practical purposes, we can already assume that the sum of 10 independent, identically distributed random variables is approximately normal. And the mean is, if the mean weight is, say, 75, then we have 750 here, and I have no idea what sigma is, but if we pick it up somewhere on the internet, the sigma for the individual, for the weight distribution, then we can estimate this other term and answer this interesting question. What's the probability that the total body weight of the passengers in this elevator will exceed 1,000 kilos if there are 10 of them in the cabin? Okay, do you understand the question? So what's the probability that the elevator crashes? I think it's exciting enough to think about this. All right, we'll discuss some examples of this at our practice classes. Okay, theorem. Suppose we have two random variables, yes, we assume that they are independent. So x1 and x2 are assumed to be independent. Now here we do not assume that they are identically distributed. Rather, we assume that each of these two follows the normal distribution law. X1 is the normal random variable with a certain value mu1 for the mean and sigma 1 for the standard deviation, and the second one is also assumed normal with mu2 and sigma 2. Question: what about the sum x1 and x2? Again, let me emphasize that here we're talking about a different situation. We do not sum up a great number of random variables. We only sum up two, okay? But we assume that each of them is normal. We assume that each of them is normal, and we assume that they are independent. Both conditions are very important. So if these two conditions are in place, then the sum is also normal. Just think of this. Summing up two normal random variables produces another normal random variable. So x1 and x2, x1 plus x2 is the normal random variable where the mean is mu1 plus mu2, this plus this, and the variance is sigma 1 squared plus sigma 2 squared. Okay? Well, actually, we know about, we already discussed this. I think it's not here anymore. But if we add up two random variables, the means sum up, and if we add up two independent random variables, the variances sum up. So this is no surprise. What is a surprise is this. The sum is normal. Okay? Now, actually, this theorem and this fact here are not disconnected. They are connected in some profound way. Again, a normal random variable can be produced by so-called, so to say, joint action of a great number of independent random variables. Okay? And suppose this one is produced, well, is obtained as the sum of, say, 1,000 identically distributed independent random variables. And this is produced as the sum of another large number, say 1,500 identically distributed random variables. Okay? Suppose we pull together all these underlying, this 1,000 and this 1,500. Suppose we pull them together. We can expect, by the same reasoning, we can expect that the sum is again normal. Do you understand this? If the normal random variable appears as the sum of a very large number independent, identically distributed random variables, then it must have this property. The normal random variable must have this property. Do you understand why? Okay. Well, it's not the only distribution law that has this property, but it's characteristic of the normal random variable. All right, now let's move on. Our next big chapter here is sampling and distribution. Sampling and estimation. All right. What are the basic assumptions here? We assume that we deal with the population. Well, it should be emphasized that population is an accepted term in mathematical statistics. By the way, we are starting the mathematical statistics part now. And population is an accepted term in mathematical statistics. And please do not misunderstand it. It's not necessarily about a human population or an animal population, okay? It can be any collection of objects. So we talk about a population and we say that the population has size and capital is more or less standard notation for the population size. Then we say that each member of the population possesses an individual value of a certain numerical characteristic. Okay? Numerical numerical characteristic. Now, what do we mean by this? If we talk about, well, the population of Moscow, each resident possesses his or her individual body height, body weight, well, income, number of children, number of years of education, the length of nose, whatever, okay? We can be interested in many different characteristics. But here we are talking about numerical characteristics. So we assume that each member of the population possesses his or her or its individual value of this numerical characteristic that is of interest to us in particular research. Okay. Now then we say this. We perform what is called a random choice. Random choice. We perform, suppose first, we talk about choosing just one member. Now, what exactly does this mean? What is random here? What random means that each member of the population has the same probability to be chosen. Simple enough. This is called random choice. Okay, then because each member possesses a certain value of the characteristic, and because we perform this random choice, we create in this way, we create a random variable, okay? And what's the distribution of this random variable? So X So if we choose one member at random from a population, the result is a random variable. What kind of distribution does it have? Well, this, on the one hand, this is a simple question. On the other hand, it's a bit subtle. Now, formally speaking, if it's a finite population, maybe it's a very large population, such as a population of a large town, such as Moscow, but still, if it's finite, then the each member has the probability 1 over n capital to be chosen, okay? And so first we notice that the random variable generated in this way is basically a discrete random variable, and because well, now we notice that maybe it's possible that different members of the population possess the same value of the random of the characteristic. For example, suppose we're interested in education in complete years. Okay, there are just so many different possible values of this, and of course, when you look at a large population such as the population of Moscow, many members of the population will have, suppose, 10 years of education or 15 years of education. All right, so what I mean to say is this. The random variable generated in this way is a discrete random variable where the list of possible values is just the list of possible values of this characteristic, and the probabilities actually are relative frequencies of the occurrence of this or that value. Do you understand this? Well, suppose there are 10 million people in Moscow, and say 6 million of those have exactly 11 years of education. Then in this list of possible values, 11 years will be associated with the probability of 0.6, okay, like this. All right, so this is just for the first step, because what we must say next is this. If the population is large, and if the characteristic has continuous nature, is continuous in nature, then we can and should approximate this discrete random variable by a continuous random variable. This is the right thing to do. This is an appropriate model. So we have a large population plus continuous characteristic. So if these two conditions are in place, what do I mean by continuous characteristic? Well, the body weight is a continuous characteristic. It can take on any real value within certain limits. But the number of children in a family is not a continuous characteristic. It cannot take on the value 1.5, for example, okay? Just some integer values. So if we talk about a large population and continuous characteristic, then we typically, okay, I write this, put this circle here. We approximate by a continuous random variable, okay? In many cases by a normal random variable, although technically speaking it's discrete. Okay, do you understand this point? Well, we almost never use this discrete. We almost always approximate it by a continuous random variable. All right, next. Suppose we make a random choice. So choose one member. Well, another thing to say this is that we perform just one observation of the random variable. So, one observation. And the observed value is denoted by x lowercase. There is a certain tradition here. The population variable, the random variable, is denoted by x capital. And the particular value that we observe is denoted by x lowercase. Okay? Well, okay, suppose we choose just one member and observe just one value. Now, what can we say about x capital? So, suppose we have no idea of this distribution, and we choose just one member and observe one value. Can we say anything reasonable about this distribution? Well, probably we can make this wild guess that the mean value of this, the mu, is not very different from the value that we observe. But what is not very different? Can we quantify it? Can we make a quantitative statement about x being close or not close to mu? How close is x to mu? Well, let me tell you that we cannot say anything sensible about this, cannot give any sensible answer to this question if we don't have any information on sigma. Okay? Well, and we can't estimate sigma on just one measurement, on one observation. Later on, we'll be discussing this technique of estimating sigma on the observations made on a sample. But if the sample consists of just one observation, we can't form any estimate of sigma. There is no dispersion here, there is just one value. Okay, but suppose we have an estimate of sigma obtained in some independent way. Okay? So suppose we have an estimate of sigma. Then, if we have one particular measurement and an estimate of sigma, we are already capable of saying something about x, about the variable. And this something follows from Chebyshev's inequality. Look at this. Mu minus k sigma plus k sigma is greater than 1 minus 1 over k squared. This is Chebyshev's inequality. Well, and we can rewrite it this way. Probability x minus k sigma, x plus k sigma is greater than of 1 minus k squared. Well, technically, it's the same inequality. We just rearranged the terms here, performing some subtractions and additions to the different sides of the inequality. So technically, it's the same inequality, but it can be easily misinterpreted. Now, what this inequality says is, given a certain value of mu and given a certain value of sigma, the probability that x, the random variable, falls within this interval is at least 1 minus 1 over k squared. This all larger, okay? Now look at this inequality. If we are not careful, we can interpret it in this way. The probability that mu gets in the interval from x minus k sigma to x plus k sigma is greater than or equal to this right-hand side. And this interpretation is wrong. And why is it wrong? The thing is, mu is not a random value. Mu is fixed. We may not know it. This is a different story. We don't know its value, but we understand that it's already there. It's a fact of nature. Okay? Mu doesn't depend on our random choice. This is the thing. So to say that mu falls within this interval is not correct. Now, what is random here is not mu, but the interval itself. The interval itself. Okay, this is mu. This is x minus k sigma, and this is x plus k sigma. Now, performing a random choice, we get this interval that can be shifted with respect to mu to the right or to the left. And each time we make this random choice, we obtain this random interval. So the right way to interpret this inequality is this. If we make a random choice of x, then the probability that this interval constructed basing on what we get on this random choice, the probability that this interval captures the true value of mu is greater than or equal to 1 minus k squared. This is a subtle difference, but it's important. These two things are very often confused. Let's give it an example. Because we have this global warming, okay, there are a lot of concerns about the deteriorating conditions for some northern animals, such as polar bears. And there is this concern that maybe they, this species is endangered, and as an indication of that, there are some indications that the mean weight of a polar bear reduces, becomes smaller. Now, before this global warming, according to what I read on the Wikipedia, the average body weight of a polar bear and adult polar bear was about 500 kilos, which is a lot. And some individuals reached the weight of 1 ton, which is absolutely huge. But that was the golden era of polar bears when we didn't have this global warming. Global warming is absolutely bad for polar bears. So we have this concern that maybe the mean weight of polar bears goes down, which may be a strong indication that global warming is actually taking place, and it's bad for the animals, for some animals. All right, suppose we stage an expedition, okay? We stage an expedition to the land of Franz Josef or Spitsbergen. I don't know exactly where these polar bears where they live. I think it's about Spitsbergen. And we organize an expedition, and the technique for measuring weights is this. We have a special kind of rifle that actually that doesn't shoot bullets, but rather it shoots kind of syringes or darts that inject a sedative. Okay, so we spot a polar bear, shoot the rifle, and the polar bear is injected with a sedative that is supposed to put him asleep, after which we approach and actually measure the weight. But it turned out that the sedative didn't work very well. The bears didn't fall asleep. Only one bear fell asleep, and maybe he was sleepy in the first place. Maybe it wasn't the sedative. So actually, finally, we only took one measurement. What I mean to say, we only took one measurement. And this measurement happened to be 110 kilos. Okay. Now, again, can we make any conclusions from this about the mean weight of the population of the polar bears. Well, no conclusions whatever are possible if we don't have any information on sigma. But, and sigma can't be estimated on just one measurement. But we say this, okay, maybe sigma is a more or less stable parameter. Maybe it can be borrowed from some field research conducted, say, 10 years ago, okay, or maybe 20 years ago. And maybe we can still use it. We search for some sources and find that a certain number of years ago, say 20 years ago, sigma was equal to 17 kilos. And we just assume this, okay? We understand that this may not be very, very accurate, but we hope that it's good for our purposes here. All right, and then we set k equal to 2 in the Chebyshev inequality. And then we write this, p x minus 2 times sigma Now, if you substitute k, 2 for k here, it's 1 over 4, and 1 minus 1/4 is 0.75, and this is why I write this here. Okay, but look at this. X minus 2 sigma is 410 minus 2 times 17, which is 376. And x plus 2 sigma is 410 plus 2 times 17, which is 444. So, with a probability of 0.75, this interval from 376 to 444 captures the true value of mu. This is not a good estimate, of course, because we only had one measurement. It's very crude, not at all accurate, but it's something. Look at this. If we know that 20 years ago the mean weight was 500 kilos, then this is already some indication that probably, to some level of confidence, the mean weight is smaller now, okay? But again, it depends on this assumption. It depends on the assumption that sigma is the same as it used to be. All right. Now, please pay attention that here in Chebyshev's inequality, no assumption is made about the law, the probability law of x, of the distribution. Okay? And it works for any distribution, whatever. For a particular type of distribution, such as normal distribution, this value on the right-hand side will typically be larger than that. So this is the lower bound. This probability can't be less than given here for any distribution. And for a particular distribution, we can expect it to be larger. And actually, for a normal random variable, this probability, the same probability as written here, is equal to is this. Okay. So if we can assume the distribution of body weights in polar bears to be a normal random variable, then to a rather high probability, the mean, we can expect that this interval captures the true value of the mean. Okay. Well, so we can, but of course this is not how it's done typically, because measuring just one weight, it's not cannot be called an extensive kind of research. Well, now that was just some extreme case. I wanted to say by this that even if we take just one measurement, we still can say something about the random variable. At least we can do it if we know something about sigma. All right, now let's talk about this. Suppose we take a sample. Now, here we just take one measurement. Suppose we take a sample of some size n. Random sample of size n. Pay attention that here n is a little letter, little n, lowercase letter. It should not be confused with the capital letter. This is a convention. The capital N is used to denote the size of the population, and the lowercase n is used to denote the size of a sample that we take from this entire population. These figures are typically very different. Okay? If we talk about the population of a city such as Moscow, then n capital is something like 10 or 15 million, and n lowercase, in practice, what kind of sample can you hope to take if you conduct a field research? How many people can you interview asking your questions? Well, if you are doing this, let me tell you, field research is a tough kind of occupation. Interviewing people is not easy. So if you actually interviewed, say, 150 people, you're a hero. Okay, it's a lot of work to do. So n lowercase, if it's something like 100 or even 1,000, it's still a very small proportion of the total population. So n capital and n lowercase are typically very different figures. Okay. So we take a sample of a certain size n. Now, what do we mean by this word here? Now, when we said that we choose one element, one member at random, this is more or less clear. Each member of the population has the same probability of being chosen. But what do we mean by the random sample? It seems intuitively clear, but let me tell you that it's not, actually. Now, the question here is this. How do we actually perform this choice? One approach is this. We choose a member at random, and then we kind of return the chosen member to the population. And the second time we choose someone, we deal with the same initial population. Okay? This is called sampling with replacement. Okay? So, at each stage in our sampling procedure, each member of the population has the same probability to be chosen, of being chosen. Sampling with replacement. Replacement indicates exactly this. After we've chosen somebody or something, some member, we return it, replace it in the population. And another procedure, but now, this procedure is very good in a certain sense. It's perfect because all the theorems of the probability theory, all the theorems concerning X bar, for example, work exactly when we do this kind of sampling with replacement. Because look at this. After we have selected the first one, we kind of return this member to the population, and when we select the second one, we deal with the same random variable. So we, as a result, we have n independent, identically distributed random variables. This is the point. This is exactly what we discussed just a short while ago. The most important theorems refer to this case. Now, there is a problem here. There is a shortcoming to this. If we do this kind of sampling, it is possible that the same member will be chosen more than once. And it's not done this way in practice. Okay? So in practice, if the same member appears this more than once, you do not interview him or her again. Okay, it's kind of stupid, a stupid thing to do. But the recommendations for practical sampling is to, if a member appears more than once, you just ignore this member, skip this, and make another choice until you have a sample of different members. Okay, and this is called sampling without replacement. Okay, now, formally speaking, in this case, x1, x2, xn are not IID, are not independent, are neither independent nor identically distributed. Because if you have chosen one guy and put this member away, your second choice is more narrow, a bit more narrow, okay? One member is excluded from it. So the second choice, the second random variable, will be dependent on the first one, and it will not be distributed in the same way. So, strictly speaking, the theorems about X bar do not apply to this other method of sampling. But this is just theory, because if your sample is, the sample size is something like several hundred, and your population size is something like several million, the difference between the sampling with replacement and sampling without replacement disappears, it becomes negligible. Do you understand this? So if n capital is much larger than n lowercase, okay, the two methods are equivalent. Okay? Do you understand this? Well, let's look again at this other thing. How many different samples are there? Well, do you remember this notation? It's read this choose this, and capital choose n lowercase. The number of combinations of n capital elements chosen, taken n lowercase at a time. So there are this many different samples that can be taken in this way. And when we say that we perform random sampling, we mean to say that with equal probability we produce any of this huge number of possible samples. Do you understand this? The meaning of the word random here in this approach is that the sample that we get can be any out of this great number of samples with equal probability. Okay? All right. And then we get sample data. So because each member of the population is associated with his or her or its individual value of the characteristic, and we select n of them, what we get is sample data. x1, x2, xn. Again, I want you to distinguish between x capital here and x lowercase. X capital is the name of a random variable. When we choose one member at random from the population, we create a random variable. We can get any value out of this great number. Now, what I write here is this. We take a sample and we get a sequence of specific values. Specific values, okay? Sample data. Now, we are going to use this definition. A statistic a statistic is a function on sample data. Sample data. So we have this sequence of numbers, x1, x2, up to xn. Any function that we define a function on this sample data, formally speaking, is called a statistic. Please pay attention to this indefinite article here. Statistics is the name of the science. A statistic is a special term accepted in the science, and it denotes any function that we define on the sample data. Now, formally speaking, it can be any function, but of course, in reality, we understand that a statistic is used to make some inferences or conclusions concerning the population as a whole. So it's not just any function, it's a function used for inferences. Now, inference is another word for conclusion about the population. All right, and also, apart from this, we define what estimator is, definition. An estimator is a statistic that is used to estimate a population parameter, such as mu or sigma. So the most common and the most often used population parameters are mu and sigma. And the whole science of mathematical statistics is basically about making inferences, and a large part of it is about making inference about mu and sigma. All right, and finally, this notation, population parameter. Well, in textbook and in theory, there is an accepted notation for it, theta, the Greek letter theta, like this. Okay? Again, theta, you can think of this as mu or sigma, but the point is, we do this when we don't know the actual values or value of mu or the actual value of sigma. This is why we try to estimate the parameters that are not known to us on the sample data. This is the whole story. Okay, just one more thing. The estimate that is used when the actual value of sigma is not known is denoted by sigma hat, and this funny symbol on top of this letter is called I'm sorry, theta hat. This is hat. Okay, thank you. See you next time.